Hello, I'm Steven. I'm a second year PhD student on the institutional Additive program. Today, I'm going to present my research, which is process property relationship and digital light processing of ceramic materials. Traditional ceramic manufacturing works well with large scale of production, but it lacks of geometric flexibility and microstructural control. That's why we are using DLP in ceramic printing, because it's based on layer by layer manufacturing, so that we can control like some microstructural properties. So also we can tune some material properties as well. So our research, basically, in my research, we are basically trying to investigate some DLP process dynamics and how we can manipulate those with some parameters. So one of the initial parameters that we are trying to investigate is exposure time of DLP. Exposure time is basically the time that we apply to each layer and to cure them in DLP. And so that our thought is, if we can change the exposure time, we can also change some material properties, like some mechanical properties, like strength, flexure, modulus, etc. And we are basically asking 4 questions in here, and they're all connected to each other. First, how does the cross-linking of polymers affect the ceramic matrix? How does exposure amount affect the interlayer adhesion in green parts? Why does the working curve is not reliable for actual DLP prints? And lastly, how the variation in exposure time impact interlayer adhesion and final mechanical properties of sintered part. So before setting the exposure time, working curve analysis is done, and it's based on like some repeated photoreology analysis, and basically it tells us, okay, this is my light intensity, and I want to have this amount of layer thickness. So what should be my exposure time? So it is a commonly used method in the literature as well, and it's based on Jacob's equation here. And also we did this analysis on our 2 types of resin. One of them is porcelain, which is a ceramic-based resin, like it's the commercial name of the resin actually. And the other one is bison-based resin, which is basically just polymer. There is no ceramics in it. And we also did this test like several times to have a more reliable results. And it turned out like to have a successful print for the porcelain, the minimum required exposure time should be at least 15 seconds. And for the base resin, it should be around 9.5. But in reality, when we try to print with these parameters, like every time when we try with these parameters, all our prints were failed. So we also we had to try with exposure time at least 30 seconds, and because like working curve was based on single layer, and our normal prints were like multiple layers. So we had to our minimum exposure time was 30 seconds, and we went up around like 150 seconds. And also we did TGA analysis during the printing to make sure that there's no settlement. So we basically took samples like before, after, and during the printing to like make sure we have like homogeneous particle distribution in the wet. And so there was no weight change, which means that like the resin was stable in the wet. And these were our 3-point bending tests. And we basically wanted to see how flexural modulus change, like when we change or increase the exposure time. And as we can see from this plot, as we increase the exposure time, there's like an increase in flexural modulus, but after a while, it's like there's a plateau. So there must be like we actually gonna do further analysis on this. Like there must be some sort of like a optimum time for exposure time for flexural modulus. And also, when we look at the strength values, we actually see a more complicated, a more complex result. And like we first analyze the strength, then we found the Weibull modulus. Weibull modulus is a statistical parameter. Basically, it tells us like if you have a high Weibull modulus, it means that your samples are like more reliable. But if you have low modulus, it means that you have a greater variability in your strength, so that your tests are not that reliable. So as we can see from this plot, there is like an increase when we go to the 120 seconds, but after that at 150 there's a huge drop. So this also again tells us there must be an optimum exposure time to have a like an optimum viable modulus, the highest viable modulus. Also, we did degree of curing analysis with FTIR, and we had four samples. The blue spectra is uncured resin, and these are also cured resin. Like we investigated 30 seconds exposure time, like 3D printed 30 seconds exposure time, 60 seconds, and 90 seconds. And we basically selected one peak, which was pentaerythral tetraacrylate, this one. It's a commonly used photocurable monomer, so we just follow that peak and see if there's any change on that peak in our printed samples. As we can see from here, this sharp peak is almost completely disappeared in our printed samples, even for the lowest exposure time, just 30 seconds. So when we zoom in this area, which is here, like we wanted to also like calculate the degree of conversion of these monomers, like basically degree of cross-linking, let's say. And we then after we did the calculation, we found that almost like that they're all almost fully cured. Even in our like lowest exposure time, we had more than 90% of degree of conversion, which means that there is no difference between there's no difference in degree of curing in the different exposure time. And we also wanted to eliminate the ceramic particle effect. So we did the flexion modulus analysis for the base resin as well. So we see, okay, it's not like the one that we have in the porcelain, the ceramic base. In the ceramic one, it was like a more clear increase. This one has a more stable, increase compared to the porcelain. So my assumption is like whatever happens is because of the ceramic particles, not the polymer side of it. Like, yeah. And this is kind of a new approach that we tried. Also, it's not really existent literature at least. And this is a photorheology setup. We wanted to see the effect of interlayer adhesion in our like mechanical properties. So we first print a single layer on a plate. Then I remove the residual uncured resin. Then I added more resin in it, and I did photorheology analysis again. And we basically wanted to see what's going to happen if we have an initial layer on the plate. Also, we did the same analysis without having an initial layer to see the effect of interlayer adhesion. So the graphs on the left-hand side, these have only one layer, and these ones on the right-hand side, they have an initial layer on the plate. So also this one is 100 seconds exposure time, 120 seconds of exposure time, and 150 seconds of exposure time. And as we can see from here, when we have an initial layer, our gelation point is shifted to a higher level, which is actually that makes sense because in our DLPs, it's actually correlated with our working curve analysis as well, because in reality we have multiple layers. That's why we need more time that we saw in the working curve, so that space tells us as we have more than one layer, we need more time to fully cure our material. So our hypothesis actually evolved around this idea. Working curve in the literature is not that accurate because in reality we have multiple layers, so it doesn't really explain what's going on in the interlayer adhesion. So right now we are trying to find other characterization methods to investigate like this interlayer addition properties of our of ceramic materials. Thanks so much.
Questions for Celine? So is printing this polymer ceramic composite the end goal? Or because I know there's some other research right now where they're DLP printing with ceramics and then further sintering it to create a solid ceramic part.
I mean, eventually, like our actual main goal is like in ceramic matrix, there are two components, right? One polymer and one ceramic. So we wanted to know what affects some like like as we can see from the data, like as we increase the exposure time, because DLP is working on like exposure time. The basically this is the main parameter that we are working on. So what's happening in that interlayer adhesion of between maybe ceramic particles and resin itself as well? What's going on so that we have this increase in flexural module? So our main goal is like not really maybe like printing a perfect material, I don't know how to explain it, but like to understand how those parameters are changing. Like what are the
But sintering is going to happen.
yeah, we also gonna try it as well.
This is basically just focus on the green part, right?
Mhm.
Understanding how we get a good green part. The next step is to see how it influences the sintered part, which there is some data out there that shows that there is an influence. Whatever you have in the green part will affect the sintered part.
Right.
And if it doesn't, then we don't have to expose it for too long, so we can get quick prints, but that portion we have not yet looked into.
What's the Lexus scale for the interface?
What scale?
Lexus scale, how big is it? Is it like millimeter?
Like for these tests, like I am doing this test as like 100 micron.
That's the entire.
No, the entire set. Okay, the tests were like these tests were was 100 micron, but samples that I produced here, they were like 5 millimeter in thickness.
Scratch to see if it potentially tell you the model in this one. The change, for example, the door from like a strongly, like having that region at the interface, something that's loosely bounded. If you do a scratch test across that boundary. It could tell you a little bit about, but in terms of mechanical properties, that's a little.
And it's an interesting idea. Would we need like polished interfaces for that, like ideas? So we can print something with a side edge that exposed layers. We can grind it a little bit to get a smoother surface. And then do scratch testing across the interfaces, and we can look at different samples that you got here, right? And maybe we can learn more about the interfacial strength that way. Yeah, that's a good idea.
So there's a question about the quality of the adherence from one layer to the next.
So that seems to be the big factor, right? Because the curing curve tells us how long it takes to generate a single layer, right? Grow a single layer, essentially, for curing. But that doesn't necessarily explain what happens during printing, which is a multi-layer process.
And when you go one layer to the next, the bottom layer that you're printing on, the exposure doesn't impact that, because you had the curve that showed that the vinyl modules dropped when you went from 120 to 150.
Yeah, if you overexpose it, something else is going to.
See, you don't get overexposure if you're putting layer by layer.
There are definitely multiple things happening, right? When you increase the exposure time, even if your layer thickness is the same. And you're way past the exposure time that is required to form that layer. Your strength keeps increasing. But if you overdo it. Well, the modulus stays about the same, flexural modulus, but the Weibull modulus drops, so you're starting getting more defects essentially.